Okay, so in the previous video, I gave you a numerical example, like a midterm studying hours. So like here, let's now generalize that like one step further. So we are going to consider hypothesis about the true population mean. I believe that the population expectation equals a certain number, mu zero. Mu zero is your choice. It is a belief. You believe that mu equals, like, say, 30 or 50. It's your belief. And also you choose the significance level alpha, right? This is another thing you need to choose. And then look at the data. What you need to calculate is the sample mean x bar, standard deviation s, and the sample size n. So, by the way, remember these numbers 1, 2, 3, 4, alpha, x bar, s, n. These four numbers are the same numbers we used to calculate the confidence level. Both share the confidence interval. By confidence interval and hypothesis testing share some similarities, and these numbers are basically playing the same role as the confidence interval. Anyhow, so you calculate these numbers from the data, and then we know in theory the x bar follows approximately a normal distribution with parameter mean given in your belief and the standard deviation coming from your data, right? This implies standardization like this. Your observation x bar will be standardized using the mean in your belief and standard deviation implied from the data. So we are going to define the standardized test statistic as t-statistic, student t-statistic, right? This is standardized sample average. And then based on your t-statistic, we are going to calculate the p-value, which is the probability on the tails. On the tails, two-sided tails outside of your standardized test statistic, standardized t-statistic, t-stat. Okay, so it can be written this way. So this is the general way, like this is theoretical one, and in the end, what you calculate is this one and this probability. That is what you're going to do. So let me give you a different set of numbers. Now, suppose that I feel like you are studying much harder for the final. So for the final exam, I believe on average students spend 50 hours to study for the final exams, right? During the final exam period, 50 hours. So I surveyed 100 students and the sample average was 56 hours and standard deviation is 20 hours. Okay, so I gave you all the numbers, right? So my belief and sample size, sample average, sample standard deviation. So then in this case, what is the t-statistic? What is the t-stat for this hypothesis test? Calculate. Okay, so like if you have not finished your algebra, pause the video. The answer is the sample average is standardized by subtracting the mean, the belief, and by the standard deviation. So follows this step. So sample average, your belief, and standard deviation equals 3, right? By the way, you may interpret this t-statistic as the standardized difference. So the difference between your observation and your belief is 6, and you standardize that with the standard deviation of x bar of the sampling distribution. So 3, the difference between your observation and belief is standardized to be 3. And then, what is the p-value here? P-value is the probability outside this observation. again, pause the video and calculate the p-value using Excel. Okay, let me show you the answer. So the standardized t-statistic is 3. That means the p-value is probability outside plus minus 3. So plus 3 minus 3. Calculate that probability. By the way, due to the symmetry, these two probabilities are always the same. So you just need one of them. Anyhow, one side probability is 0.135%. So if you add two tails, it will be 0.27%. Okay. Now you need to compare this p-value with the significance level. Suppose you choose significance level of 1%. Then, do you reject your belief or not? Make the decision. So, when you choose the significance level to be 1%, that means you are going to reject 1%, top 1% suspicious outcomes. But your outcome is top 0.27% suspicious, much more suspicious than your standard. So you are going to reject the null hypothesis. If the p-value is too small, smaller than the significance level, you are going to reject the null hypothesis. Okay. So then I would interpret it this way. I believe that the true mean is 50 hours. And I observed 56. And I tried to think that the difference, 6 hours difference, was just a random error. To keep my belief, I have to assume that the difference 6 hours must be a random error. However, if that was just random error, so like to have that much difference, that means I had to be really lucky to meet many hardworking students, right? How likely is that? I calculate that probability. That is only 0.27%. So the difference of 6 is very, very unlikely random error, right? It is not random anymore. Then you cannot just excuse it as a random error, but I have to admit that my belief was wrong. So I changed my belief. So it is this much. 6 hour is as a random error is too large. We don't see that much random error. Random error is usually around 0 or close to 0, but 6 is too much. Okay, that is the intuition behind it. Okay, so I described how it works in simple and general case. So so far, basically, the decision is made based on the p-value. That is the fundamental decision rule. I calculate the p-value and then compare that to the significance level. That is what I explain, what I recommend you to understand as the underlying principle. But actually, there are two other ways and different ways to express the decision rules. Mainly, you may think it this way. So in textbook, I teach you as based on the p-value. That is okay. But on program, if you use a program like software statistics program, there are different commands. So, and when you write a program, you may write the equivalent decision rule in other ways. So I'm going to explain other commonly used decision rules because you may need to use them in like programming or in another course or in presentation. Different numbers may be given instead of p-values. Other numbers may be available. Then you have to make a decision based on different measures. So the three decision rules are based on p-value, which is what we learned so far. And second, t-statistic, the standardized difference. Okay. And third, critical value. This is a little new here. So, by the way, all these decision rules are equivalent. No matter what you use, the decision must be the same. The basic principle does not change. But as I said, it is a way of presentation, right? Instead of, like, for example, in some lecture, in some research, instead of p-value, they may give you t-statistic. That is possible. Or you may need to use critical value in your program, right? So depending on situations, you may need to switch between them, but they are mathematically equivalent, right? So way of expression. So p-value approach is exactly what we have done up to here. So we are going to calculate the sample average. By the way, we limit our example to population expectation. We are testing whether our population expectation equals to something. So that is the basic structure we are studying. So first thing is to calculate the sample average from the data. This is our test statistic. And second, we are going to standardize the difference between the sample average and your belief, and standardize with standard deviation, right? And based on the t-stat, you calculate the outside probability on both side tails. So calculate the p-value. This is the p-value. Probability smaller than minus t or greater than plus t. Okay? And then finally, this is your final product, and you make your own decision based on the p-value after comparing this to the significance level. So simply reject the null hypothesis if the calculated p-value is smaller than the significance level. Okay? This is, as I said, what I taught you. Also, that means you don't reject the null hypothesis if p-value is greater than the significance level. Okay? So this is the basic approach. However, what I'm going to do is, for example, equivalent, instead of based on the p-value, you may utilize the t-statistic directly. Instead of calculating probability and then compare it to alpha, I am going to convert alpha into a number that is comparable to t. That is also possible, right? So skip this step, but bring alpha to this level, right? Before doing that, so the p-value is the measure of suspiciousness, how likely your belief is true, or likelihood of the observation if the null hypothesis is true. Okay? So, and remember, to calculate the p-value, you need x bar, standard deviation, and sample size, right? Right? That means if you have different data, different realizations, your p-value will change. So even if you use the same rule, but you apply the same hypothesis testing to another group of data, then your p-value will change. So then you have to rerun your program. But good thing is, it does not need to know alpha. That means, for example, in your situation, if you do not change your data, but you would like to change alpha depending on situations, in that case, p-value is very convenient because the same data, you have the same data, so you calculate p-value once. But what changes is your strictness, your significance level. Then, given the same p-value, just compare it to your own alpha. So it will be easier to program that way. So usually in a statistical program calculates p-value for you, and then it is your choice how much you are going to reject. So alpha is your choice. So given the p-value, compare that to the significance level of your own. How much you want to be strict. So it's a basic method. But and finally, here alpha does not change the p-value. So p-value depends only on the data. And then that means it is easy to compare the role of what happens when alpha increases. When alpha increases, remember the decision rule is like this. If p-value is fixed by the data, and if p-value is smaller than alpha, you reject. So you can avoid rejection only when p-value is greater than alpha. So alpha is a kind of bar, standard. So if your data is above that, you don't reject. But if your data is below that, you have to reject. So if you increase alpha, that means you're increasing the bar. So more likely to reject because your data will be, if your data was here, and like now, your data is above the significance level, so you don't reject. But if you increase your standard, it is below, so it is now rejected. So higher alpha, more rejections. Okay, so keep that in mind. So then, in other words, if you reject something at 1%, then automatically you're going to reject the same hypothesis when at 5% and 10%, right? So vice versa, if you could not reject something at 10%, then you will not be able to reject the hypothesis at 5% or 1%. So it's a hierarchical order. Okay, that is approach number 1. So let me show you approach number 2, which is t-statistic approach. As I said, instead of there are only 2 steps. There used to be 3rd step to convert t-statistic into p-value, by calculating the probability. But instead of doing that, we are going to compare t-stat directly with something else, not alpha. So calculate the t-stat, and remember the t-statistic is standardized difference between sample average and your belief of the population mean. So this is the difference of interest, and then intuitively we are going to reject the null hypothesis if the standardized difference is too large. By large, I mean the absolute value of t is greater than something. So plus or minus large in both sides, both directions, right? So if the absolute value of the difference is larger than a cutoff, then you are going to reject the null hypothesis. Similarly, so if your difference is within plus minus the cutoff, then you are not rejecting your belief. So intuitive, okay? So then, what we need to do here is, we need to choose this cutoff, A. How do we choose it? So this must depend on this alpha. So as I said, what we do here is, we bring alpha back to this level. So alpha is compared to this probability, but we convert that probability to a number here. The clue is like this. We know this is standardized normal distribution. So we are going to convert alpha to a value in standard normal distribution using standard normal distribution. Okay? So then put it this way. So significance level alpha is a probability. What you want here is, we would like to, so when alpha equals p-value, that means both sides, each side tail probability is alpha over 2, right? So alpha probabilities are rejected, and that means top alpha over 2%, bottom alpha over 2% are rejected. So what we want is the cutoff that have tail probability alpha over 2. So remember, we represent that value in this way. Standard normal distribution, lowercase z, subscript probability alpha over 2. So then this stands for top alpha over 2 probability value. So you get this. So if alpha was 5%, we are looking for these two cutoffs that give you 2.5% on each tail, right? So then the decision rule can be stated this way. You are going to reject the null hypothesis if the absolute value of the standardized difference is greater than the z alpha over 2 plus z alpha over 2, right? And if your standardized difference is between plus minus z alpha over 2, you are not rejecting the null hypothesis. Like this explains the video. So also remember, this graph was used for confidence interval. Idea is similar. At the time, I explained 2.5% is the error probability on each side. Similar. So here, 2.5% is the rejected innocent observations. They are innocent but rejected. So it's a kind of error, right? So confidence interval and hypothesis testing are pretty similar in that sense. Okay. So, and as I said, p-value decision rule and t-statistic decision rule are equivalent, mathematically equivalent, right? So it is clear p-value can be written in this way. So if t-statistic equals the boundary cutoff, exactly you happen to hit the boundary, p-value will equal alpha. So these two decision rules are equivalent. So if t-statistic is rejected, p-value will be rejected too. Vice versa, okay? So they are identical, constructed to be identical. And also, when you calculate the t-statistic, what you need is the same data and the null hypothesis, because you just need standardized difference, okay? But it does not depend on alpha. So these properties are similar to the p-value. Basically, it is kind of incomplete product in the process of manufacturing p-value, okay? So, and then you may say the same thing. Increase in alpha makes this z smaller so that you are going to reject more. So, right? So if you increase this probability, alpha is 5%, then you have here near 2. But if alpha increases to 10%, then what you have to do is you have plus minus a should shrink, more narrower. So, and there should be more tail probability. So if that probability increases. So higher alpha makes a close to 0. So you have very small interval on which you don't reject the null hypothesis. That is consistent with our intuition. What happens when alpha increases? Okay, so also common numbers. 10%, 5%, 1% correspond to these numbers. And remember, these numbers are identical numbers that we used for the confidence intervals. Okay, because they are from the same picture, same graph. Okay, this is it. There is, in the next video, I'm going to show you the third approach, which is quite different from these two approaches. So we will use that a lot more often in chapter 10. And then after that, I'm going to give you some exercise with more realistic example. Thank you for watching. See you later.